Hi, so this video we are going to talk about the computer simulation and layout of a CMOS Op Amp with NMOS input stage. So this is the basic structure of an Op Amp. This Op Amp consists of three basic parts, which are differential amplifier, common source amplifier, and also biasing circuit. This part is differential amplifier, which consists of M1, M2, M3, M4, and also M5. Differential amplifier can give the op amp a high gain, and it is immune to environment noise. For common source amplifier, this is the part for common source amplifier. It consists of M6, M7, and capacitors. Common source amplifier will give the op amp a maximum output voltage swing. And then for this compensation capacitor, it will lower the gain at high frequency, and it will maintain the stability when the resistive negative feedback is applied to the op amp. For the biasing circuit, which include M8, M5, M7, and the current source, it will establish an operating point for all transistors to operate at its saturation region. So now we are going to talk about the calculation, how we design an op amp. We are using a 130 nanometer technology, and then these are the parameters that we extract from the data sheet. This is the conducting parameter for NMOS, and this is the conducting parameter for PMOS. This is the op amp design specification that is given in the assignment. The supply voltage is plus minus 1.2 volt, and the bias current is 150 microampere. The load capacitance is 200, and so on. So next we are going to design the aspect ratio for each transistors. As you can see, the phase margin specification is 60 degree, and then the compensation capacitor, we can get it from this equation. And then finally we get 44 picofarad compensation capacitor. And then the current flow through the M5 is determined by the slew rate. So as you can see, the equation I5 equal to slew rate times the compensation capacitor, and then we get 30 microampere. Next, the M1 and M2 is designed from the unity gain bandwidth and the small signal transconductance from gate to channel. So, and also from the equation, we get GM1 equal to 414.69 micro Siemens, and then finally we get aspect ratio for M1 and M2 equal to 7.24, which is approximate 7. And next, the total output swing will be more than 2 times with bracket VDD minus V overdrive 6 minus V overdrive 7. And then so following the calculation, finally we will get V out max equal to 1 volt and V out minimum equal to negative 1 volt. This is the total output swing. So step number 6, we want the input common mode voltage range is more than 1.6 volt, and therefore we let the V in max equal to VDD minus VGS3 minus VT1. So we will get 0.8 watt, and V minimum we will get negative 0.8 watt. And then how we design M3 and M4? We design it from the maximum input common mode voltage range, which is V max minus equal to VDD minus these equations, And then finally we'll get 8.44, which is approximately to 8. For M5, M5 is derived from the minimum input common mode voltage range, Vin minimum, and also from the equations we will get it is approximately to 4. This is the M6 parameters. M6 from GM4 we will get GM4 equal to 292.01 microsiemens, and then for a 60-degree phase margin we know that GM6 is more than 10 GM1. So since we already get GM1, so we just times GM1 with 10, so we will get this answer. And then by assume GM6 equal to this value, and then GM4 is equal to this value, and then we can calculate the aspect ratio for M6, which is approximately 536. For M7, it's actually the same from the last one. This is the equation for I6, and then to balance it, I7 must be equal to I6, so I7 is equal to 1 milliampere. So we will get the aspect ratio for M7 is 133. For M8 is derived from the M5, so the aspect ratio for M8 is equal to 20. And then next, the equation must be satisfied for balance condition. So finally what we get, this one is approximately to 66.5. So it is satisfied. That means our calculation is correct. Lastly, to calculate the open loop voltage gain, AV, for the first stage gain, AV1 is equal to GM1 over GDS2 plus GDS4, so we will get 37.87. Second stage is GM6 over GDS6 plus GDS7, so we get 26.78. So the total one is AV1 times AV2. So finally we get, then we convert it to decibel, which is 60.112 decibel. So this is the summary table of the aspect ratio of each transistor. This is the aspect ratio that we have calculated, and length is fixed because we are using 0.13 micrometer technology. So by calculation, we can get the width of each transistor. So we are using this aspect ratio to design the schematic using the computer tool.
Now we will verify our design using the Mentor Graphics EDA tools. First of all, we will run through the DC operating point and AC simulation. This shows that we run the DCOP and AC simulations. After we run through the DCOP simulation, it shows that all the transistors operating in the saturation in order for amplify the input signal. And after we run through the AC simulation, it will come out with the frequency, the graph for the frequency response for the op amp that we designed. From here, it shows that our gain is 60 dB, which is equal to 1000 gain. Now we need to verify the phase margin for this curve, so we click this one. So from the curve, it shows that our phase margin is 68 degree and the unity gain bandwidth is about 3.43 megahertz. After that, we will run through the slew rate simulation. So during the slew rate simulation, we need to use the pulse signal, and the inverting input is connecting to the output. So after we run through the simulation, this is the curve to determine the slew rate. So now we need to find the slew rate for the output. So from here we can see that the slew rate for this output is equal to 570k per second, which is equal to 0.57 volt per microsecond, and it satisfies our specs, which is equal to 0.5 volt per microsecond. Next, we'll run through the output swing simulation. So after we run through the output swing simulation, from here we can see that this is the non-inverting input and this is the output signal. So from here we can see the peak-to-peak value for the input voltage signal is 2 mV, while the output signal is 2.02 volt. So when the output value is divided by the input value, so the gain is about 1000, which is equal to 60 dB. This shows that it satisfies our design specification. After that, we will run through the input common mode voltage range simulation, and this is the result that we get. So at here we can see that the current at M5 is almost constant. So the result that we get for the minimum input common mode voltage is negative 0.8 volt, while the maximum input common mode voltage is 0.8 volt. Lastly, we will run through the differential output voltage swing simulation. So from here we can see that when we apply a very small input signal, so we will have a very large output voltage swing for the differential. Now we will compare the result between the calculation and the simulation. For the open loop voltage gain, the calculated value is 1000, which is equal to 60 dB, while the simulated value is 1065, which is equal to 60.55 dB. For the unity gain bandwidth, the calculated value is 1.5 MHz, while the simulated value is 3.5 MHz. For the phase margin, the calculated value is 60 degree, while the simulated value is 65.03 degree. For the slew rate, the calculated value is 0.5 volt per microsecond, while the simulated value is 0.53 volt per microsecond. For the input common mode voltage range, the calculated and simulated value is the same, which is from negative 0.8 volt to 0.8 volt. For the output voltage swing, the simulated value is same as the calculated value, which is from negative 1 volt to 1 volt. For the compensation capacitor, the calculated value is same with the simulated value, which is 44 picofarad. This is the layout for the design op amp. So for the input stage, we drawing the layout by using the common centroid method. The common centroid layout is generally used with differential pair. It is a matching method in which the two transistors of the different pair are symmetrically laid out about a certain axis. This guarantees that both transistors see the same process variation, so they should be matched under all conditions. After the simulation has been drawn, we run through the DLC, LVS and PEX process so that the layout that we draw is compatible with the process technology and exactly same as the schematic. In conclusion, the design two-stage CMOS Op Amp operates at plus minus 1.2 volt power supply. For the parameter that we gain from the simulation, the gain is 60.55 dB, which is 1065. For the unity gain bandwidth, it is 3.5 MHz. The compensation capacitor that we use in the simulation is the 44 picofarad, and the load capacitor that we use is 200 picofarad. The phase margin obtained from the simulation is 65.03 degree. For the input common mode voltage range we obtained from the simulation, it is from negative 0.8 volt to 0.8 volt. For the output voltage swing obtained from the simulation, it is from negative 1 volt to 1 volt. The output slew rate obtained from the simulation is 0.53 volt per microsecond. That's all. Thank you.